Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this little lab discussion, we're going to be discussing very briefly boundary value problems, what our techniques are, and then our problem to work for the day. So we have three techniques that we are using for boundary value problems. These are not the only ones available. These are just the ones that we've discussed. And the first one of these is the shooting method, which is essentially a guess and check technique. So you recreate the problem as an initial value problem where you are guessing at the initial value of the extra derivative or the extra variable you create. And then you solve and see whether it worked, and then use those guesses to refine your answer. When you've got a linear equation, it actually just, if you use 2, you should be able to interpolate and it'll get you there. But when you have more variable, or not more variables, when you have a nonlinear equation, it may take more than that. Finite differences uses an approximation where you say that the delta is just simply, say, a t of I minus t of I minus 1. And the second derivative, that would be over delta x. And the second derivative would be, the t of I plus 1 minus 2t of I plus t of I minus 1 over delta x squared. And you can go through and either create or look up those formulas for any number of derivatives. The nice thing about that is that you just get a system of linear equations. They are just a huge mess of equations. And you can set those up in matrix form and then use matrix inverse techniques to get an answer fairly quickly. Eigenvalues and eigenvectors, a bit more complex. I'm not even going over the math. I'm trusting that you have done that elsewhere. But the hard part of that technique is that you have to solve for the lambda using the A minus lambda I matrix times x equals 0. And so solving that using our matrix techniques really isn't that hard. And so therefore that technique is also a possibility to use. Now the problem we're going to look at today, I wanted to look at mass transfer. And diffusion is a key concept behind mass transfer. It is a quantification of the net movement of a molecule from a region of high concentration towards a region of low concentration. And we quantify how well this happens using a diffusivity. So it's D sub AB, and it says how well molecule A moves through molecule B. If you have a reaction in a field of diffusion without having any movement, so you're not like blowing on the surface or it's not in a flow field of any sort, then in those cases, we can get a fairly simple differential equation. Motion makes it much more complex, so we're not doing that. So in a still medium, the reaction rate is going to be slowed down by the inability of the product to move away from the reacting surface. So we have to wait for the molecule to get out of the way, the product molecule, so that we can have a reactant come to the surface so that it can react, right? There's just, a block there. And so this diffusion is going to be very important to the rate of reaction. Well, the differential equation that describes this is negative derivative of z, or derivative with respect to z, of the diffusivity times the change in concentration with z, minus the rate of formation of A, which is 0. Now, minus R sub A is also called the rate of disappearance of A. And in a first-order reaction, this would be constant K1 times Ca. And if we did a second order, it would be a different constant times Ca squared. And our boundary conditions, well, at the surface, at z equals 0, it's the concentration of the surface. So Ca naught, some value we would know. And if you move away from that to wherever this diffusion, is going towards, then typically we're going to have that be no A. There is none of the reactant A. And so therefore, I have a boundary value problem at z equals 0 and at z equals delta. So what I want you to do is solve a problem. I've just made up some numbers, okay? The film thickness is 0.2 meters. The initial concentration is 2 moles per liter. Diffusivity, 5 times 10 to the negative 6 meters squared per second. Now, K1 is going to have different units, whether it's first or second order. Just use a number 0.3 and trust that the units work out. I made it up, so it's not a real problem. And then what I want you to do is solve this using at least 2 of our methods for the first order and again for the second order reaction, and see mathematically what changes, and then present your results in a graph. Okay? If you have questions, get in touch with me or work with your classmates. Thank you very much for your time.